As I said, these are the. Are you okay, Sasha?
Yeah, yeah.
Fine. So hello.
Well,
So, review today. Is this, very briefly. So using the picture of a ramified cover, of X to a copy of P1, I'll again draw the picture, make a point not on X. And we have the mapping to Z1 equals 0. And someplace in there, let me just get the picture on the board that we've had there for two times. If you're not bored, it's a beautiful picture. So X is somehow here, and there will be ramification points here, where X is given by a special equation that makes life easy, so-called Fermat equation. We saw that the topological Euler characteristic of X can be computed as 2 times, well, let's say, the topological Euler characteristic of the base times the fiber, so it's D times the topological Euler characteristic of the base. I call this the base of this thing, so this is the base. D times it because you have D triangles, but you make a mistake, so this is a so-called ramification index. And a number of you were not terribly satisfied because this uses special triangulations and so on, but for a moment let's just see what that said. That says that the topological Euler characteristic of X, which is known to be 2 minus 2g if you believe the handle-body decomposition of X. So from the handle-body decomposition, if you believe this, it's true. Where G is the genus, G is the number of handles. And if you believe all that, which can be easily proved using algebraic topology, then you have that the genus of X is equal to a beautiful expression here. So that's called the genus formula. Opik was not skeptical, but it just didn't, and Jasper and I talked about this a lot also. You know, just covering these things with triangles and you need to prove a lot to prove that this is well defined, but it is. Okay. And Euler, I think Euler at least had ideas of proofs of this, so that's very, very nice. And this thing is this left-hand side. So this is the left-hand side of the equation. Is topological information, or geometric information if you like, And the right-hand side is combinatorial degree information. So it's very interesting. Degree of involves degree of an equation. To me, I've always found that really beautiful. And so that was, since we proved that, that motivated me, also your questions, motivated me to better understand the genus G, how to better understand that. And, right? Various definitions, how we should better understand that. And that led me to give a quick explanation, quick remarks on the fundamental group. This thing's called the fundamental group. Of X. And these remarks are the beginning of the subject which is called algebraic topology. And this is something that everybody should understand. And in general, I recommend see Alan Hatcher's book. He has an early chapter on that book. I looked at it this morning to make sure I'm right about this. He has an early chapter on that book on the fundamental group. And it's nice. He has examples and so on. So what is this fundamental group? How to think about it. X. And then you can, I'll repeat this from last time. Last time my notation was really bad, so let me try to be precise with some notation. And what I would like to, so we have, in this case, we're talking about a Riemann surface, and you fix a base point in the surface, which actually is not going to be important in the discussion, but we're going to talk about the fundamental group with base point x0. It doesn't matter which base point it is if the manifold is connected. So just pick some base point and then discuss the matter. And what the first thing to do, and it's very good language, is to consider loops, closed loops at, well, I draw a beautiful closed loop, it could be terrible, at least piecewise continuous or piecewise smooth even. So closed loops, you consider closed loops at the base point x. So L of, let's say x0, I'll call this L for now, is the so-called loop space based at x0. So this is a so-called loop space. And in modern physics, loop spaces are very important from the point of view of string theory and so on. So that is a very important space in itself. All of these loops, it in fact is, can be called a loop. It's a space, but it's even a group. Because you have, as I explained last time, the possibility of composing two loops. Go around the first one, then go around the second one. The operation, in case you want to know the word, is called concatenation. Putting two loops together to get a single loop is called concatenation. It's a funny word. I only know it in English. I think it's a German word also. So it's called the loop group. And if you have the loop space, you have one loop, let's say L1, and another loop L2, you might ask yourself if you can connect the two loops. Right? Loops, yeah. Well, if you're lucky, you may be able to, but you might not be lucky because you might have other components. This loop group might have many components, and then there will be the connected component containing this L1, and you ask if you can connect that to L2. Okay, and of course, connecting one loop to another, it means homotopy of the loops. That's a curve of loops. You can imagine this. It's a curve of loops. You move the one loop into the other loop by a homotopy. That's what I told you yesterday. It's called a homotopy of the loops. All right, and so you're interested in a special component, L0, let's call it, equals the loop set of loops which are connected in this sense, and so I'll use the word homotopic, to the constant loop. In the picture here, that is completely obvious. If I took, here's x0, I mean, I can obviously homotopy this thing, just squeeze this thing down to the point in this case. I can do it in that case, but of course, there is no way that if I take this thing here, that I can homotopy that over to the constant loop. Well, maybe I should start it someplace. I should start at x0. I promise you, start at x0, go around this thing, and go back. There's no way I can homotopy that to that. And so we're interested in this L0, the homotopy equals. And so what we do is we mod out by this, L modulo homotopy, and this thing is the fundamental group of X. That's it. Okay. Now the amazing thing is, I mean, you can imagine, you don't have to be some genius to imagine how big this loop space is. I mean, there's a huge number of loops. It's an interesting infinite dimensional space, but it's really big. And this thing is, so X here is the compact manifold. Let's say connected manifold. It has nothing to do with complex analysis at this level. This is just this thing is here. This thing is here. Then a countable group. So there are only countable many elements here. It's an amazing thing. It's countable in the sense of you count the number, and it's a group. It's a countable group. And then, yes?
Would we also then say that two loops, when they are retractable to the same loop, are also equivalent?
That, of course. I mean, this is this group quotient that I just made, and that's you just write down. That's right.
Because not all loops might be contractible to something constant.
That's right. Right. But the formalism is just mud out by the homotopic loops, but that's the same thing as saying two loops are equivalent if they're homotopic to each other. And it's an equivalence relation. It's just a question of modding out by a normal subgroup. It's just a question of, is that really an equivalence relation? And your question was about is it transitive? If X is equivalent to Y, is Y equivalent to Z? I think that might have been your question, right? Then X is equivalent to Z. So yes, all of those things, because that's just Okay, so that's that thing. And then there's an example that I was mentioning after class the last time that's very, very, very interesting. That if X is a non-compact Riemann surface, of course, maybe its fundamental group is even trivial, but then the fundamental group of the non-compact Riemann surface is a free group. And maybe since you don't have experience with free groups, you have experience with freedom, but not with free groups, the free group Fs on a set of generators S. Okay? And I have to tell you what that means. That means that the elements of the group G, so G an element of this free group, then that means that G is just a product, a finite product, some M arbitrary, but finite, and these SIs will be in the set S. So it's a formal construction there, that's all it is. Just, and this thing here, this formal construction is called a word. Now you can, of course, if you have a bunch of S1s together, you can write it as a power. So you can write this as S1 to the N1 times Sk to the Nk. But there are no relations. Like S1, S2 equals S2, S1. That would be commutivity. There are no relations here. So it's on a group of, it's on a bunch of words with no relations whatsoever. You can write this down formally. And the amazing thing is, if you have a non-compact Riemann surface, it's always a free group. I think this is a serious theorem, and I think the first really nice proof that I understand is by alpha. So it's not that old of a theorem. That's it. And for example, a concrete example that I always mention to everybody, I mentioned last time, I'll write it again. If you take the complex plane and you remove 2 points, my favorite points, 0, -1, and +1, then, so minus sets plus or minus 1, this is X. So minus complex plane minus the set, this should be X. And then the fundamental group is generated by 2 letters, S1 and S2. And the fundamental group is a free group generated by S, where S is just these 2 letters. It's very interesting. Okay. So that's the fundamental group. Okay. And as I mentioned last time, if some motivation for what I write, modding out the commutator group, some motivation for this that maybe comes even from Riemann, is that if you want to integrate a holomorphic form, for example, over this product of curves, this is a curve where you can integrate. This is, by definition of the integral over A plus the integral over B minus the integral over A minus the integral over B. By by definition, this has to be this for the definition of the integral, and that's 0. So that means that the integration over curves really never recognizes commutators. And so that motivates you or Riemann or somebody to define the commutator subgroup of the fundamental group. And this is the group generated by the commutators, subgroup of the fundamental group generated by the commutator. Commutators, this is a commutator here. Generated by the commutators. You can always do this and write this group down. And this thing is a normal subgroup at least it's not here, but at least likes normal subgroups, because this is a normal subgroup of the fundamental group. So we can you can mod out by it. It means the quotient fundamental group modulo the commutator subgroup is again a group. Is again a group. And this group, by the so-called Hurewicz theorem, is what is called the first homology group of X, whatever that is. Whatever that is. But forget it, you can just take that as a definition. But that's the theorem in the subject of algebraic topology, that you have this isomorphism. And so it's, of course, whatever that is, this I defined rather carefully. And now finally the theorem is, this is z to the 2g power. Just in case of some confusion, that means that z cross z cross z cross z cross z cross z cross z, 2g times. Okay? So that is a clean definition of z. I mean, people are complaining, Euler number and this and that, all these triangulations and all this stuff. That is a very, very clean definition of g. Okay? So, okay, and you can imagine for this, here the homology group, so here the homology group, after you've mod out by this commutator, is just z cross z. This thing generated, this thing generated. What you see is what you get. Integration is okay. That's it. So that's, I think, a clean definition of everything. I think you should be satisfied. Okay? That's still reviewing. I know this is a lot of review, but I know also these things are new for you, so it doesn't hurt. So we have a clean definition of G. And then the second thing that needs to be reviewed is Riemann's count. I formulate this in a rough way because Riemann, I'm not sure what he proved, but the statement is, and I will not make this precise, there is a complex manifold. Manifold depends how you look at this thing, so don't worry about, you might have to worry about singularities here. Maybe this, let me write here, space. So you might have to worry about singularities, which, let me call this mg, which exactly parameterizes the Riemann surface of the genus G. mg, the m here, you will you will hear the word moduli often in this subject, and this was used by Riemann himself. So you should have the feeling that that's what it is. There's a complex manifold, or maybe with singularity sometimes, that exactly parameterizes it. Yeah.
So parameterizing means there exists a projection between or holomorphic?
So this is a delicate question. He's asking, what does it mean parameterize? Okay? That means, so let me give you the very sort of primitive statement, okay? It says, look at all the set of X, such that X is a Riemann surface, I'm tired of writing this, of genus G. Okay? I'm not a good logician. I loved logic when I was young, but I hope this is a set. I think it's a set. You know, the problems, this looks to me like a set, maybe. Okay. Modulo equivalence. So, and equivalence means stupidly, there are two things that are equivalent, if and only if there exists a phi from x1 to x2 or vice versa by holomorphic. That's the obvious thing. Okay, that's an obvious thing. Right? That's some set. That's some set. And what I'm saying is that this is by definition Mg. Okay? This is, if you like, the definition of Mg as a set. But what Riemann knew and what modern mathematicians have proved, this is a complex manifold or space of dimension 3G minus 3 with certain key properties. I don't want to get into it, but you can think of it as a beautiful complex manifold of dimension 3G minus 3. It gets very big very quickly. For genus 3, this is already 6. So, very interesting thing. And let me emphasize, right underneath this, look at the set of all Riemann surfaces. I'm going to write it again, just for drama's sake, of genus G. Let's call this H for holomorphy, H for holomorphy, H for holomorphy of genus G. Of genus G modulo H for diffeomorphy, where here I have the equivalence relation. The diffeomorphic equivalence relation means that there exists a diffeomorphism, diffeomorphic, from x1 to x2. You can ask two questions. Yeah? Two questions. The first answer is Riemann and modern mathematicians made it precise, say that this is a manifold, complex manifold of dimension 2G, and this is exactly 1 point. Right? That's fundamental. That's fundamental. We were talking yesterday to Jasper. He said, why is that fundamental? Why is it important? It's important because we need quite often in applied problems, we see the parameters of the complex structures moving. I even know examples in the study of waves and various other interesting examples. You see the parameters of the complex structure moving in this parameter space. Yeah. In string theory, you will see these moduli spaces play a role in string theory, and all these people go blah 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 string theory and all this blah blah blah. But what it is you're talking about these spaces are very important. These moduli spaces of structure. Okay. That's the second thing that I mentioned. That's Riemann's count, that's 3G plus minus 3 dimensions. And then the question 2, say A, is how many do we get? It's a rough question, so I write rough English in P2. Okay. In other words, you start out with this is a curve of genus G, so I write it in the space of all curves. Here's a curve of genus G, let's say X, a curve of genus X, maybe genus, let's say degree D. And now I'm going to move this in the space of curves of, this is the space of, inside the space of curves, inside the space of curves of genus, space of curves, degree D, I'm going to move it. It's obvious how I move it. I just move the polynomial, right? So, in other words, we start, for example, we start at a base xf for Fermat. This is given by the Fermat polynomial, z1 d plus z2 d plus z3 d equals 0. That's a wonderful Riemann surface. We know what its genus is. And I make the movement, that's the Fermat, maybe this is Fermat here. I make the movement to nearby things. And so a nearby thing might be, and I'll tell you a very beautiful family in case you're, let me tell you a beautiful family. It's harder to write for D, but here's a beautiful for D equals 3. I'm going to make a beautiful movement. I'm making a beautiful movement. I start out with a cubic of Fermat. Cubic of Fermat. And then I take another cubic. So here's Fermat, it's a beautiful cubic. What is it? Cubics? Oh, it's a torus. It's a torus. And then here's another cubic, Z1, Z2, Z3. And this is 3 lines equal to 0. These are 3 lines. And now, well, I make a 1-parameter family that I call this zeta 1, and I call this zeta 2, and I'm moving as zeta 1 and zeta 2 move. So this is, you see, I'm moving here with the parameters zeta 1 and zeta 2 in projective space. This is a movement inside the space of curves. Now this is a movement. So here we go, here we go, here we go. And at the end we have a horribly singular curve, which is just 3 lines. But in between we get regular curves, and then almost all of them will be different. So that will be a non-trivial movement in Riemann's moduli space, and that's very interesting. So I can start with Fermat, and I can move, and I can get, there's a 1-parameter family, I just wrote one down. And here's another parameter family, another, okay, the question is how many can you get? And you don't come close to getting everything. That's what the calculation was that I did last time. Okay, so the Riemann number is 3g minus 3, and the number of curves, well, I wrote it down. Here we go. Here's the homogeneous polynomials in a degree d in 3 variables. I have to make a projector because I don't care about multiplying it by 100, and I have to subtract off symmetries. So I know that we get at most this amount. And this amount up here, we know by the genus formula, is this amount. And if you do the calculation, you could lock yourself in the closet and do the calculation, and you can see that this number is a huge amount bigger than this number. Oh, the other way around. This number is a huge amount bigger than this number, right? So you get, Riemann gets far more Riemann surfaces than you can find in P2. That's interesting. And they really occur, and it's extremely interesting that. Okay. Let's still review sorry there's so much review. And now finally, maybe my third point in this review is, why do I care? Why care about embedding Riemann surfaces someplace, for example, x in P2 or maybe you're lucky x in P3 or wherever you're going. I don't know, various possibilities. Why do we care? Okay. Why do you care? And one reason to care is the word restriction. That's exactly the reason to care. So here's the situation. You have, let's say, some space y, and you have x sitting inside of y. Maybe I draw it as a Riemann surface. So you have x sitting in y, biholomorphically in y. And it is completely clear that what you should try to do at least is take an object on y, let's call it object y, and you restrict it to the same object, but on, I dedicated some of my remarks to you, but it's too bad you missed it. You can restrict the same object, but restrict it to x. Isn't that true? Like a function. You hope you can restrict stuff. At least functions, this is okay for functions. This is okay for functions, and this is okay for differential forms. Isn't it true? You take a differential form on the ambient space, you can restrict it. Right? But there's some things that you can't restrict, it goes the other way around. If you have a curve in y, you can't restrict it to x. Right? But if you have a curve in x, you can regard it as a curve in y. So some things restrict, and some things go the other way. I just mentioned curves go the other way. There's fancy language for this kind of mathematics. You have the restriction morphism or the other kind of morphism. Okay. So in this case, at least for functions, differential forms you can restrict. And in particular for meromorphic functions. So meromorphic functions. Functions should restrict. You have a function. So let's talk about the case if y is equal to P2C and x is equal to a Riemann surface of degree a curve of degree d. Why not? Then if you have a meromorphic function on P2, then you can just restrict whatever that means. Then you can restrict it to x as a meromorphic function. And I'm going to write here caveat, if you're lucky. If you're not unlucky. So this is a statement. It is a good statement because we're going to find a lot of meromorphic functions on P2, and we don't know what the devil's going on with x yet. Right? So just let me remind you, if we have x as a non-compact surface in, say, I told you it goes in C3 all the time. it is completely trivial to take power series on C3 and restrict them to holomorphic functions on X. That's completely trivial. Anybody can do that, right? But there's some danger with this. Why is that? Maybe the polar set of the meromorphic function that you're restricting contains X. Can you imagine? You're restricting something, the whole polar set is X. So you're restricting something that's identical. It might be terrible. You get what I'm saying. So maybe you don't get it yet. But it could be in principle. Right? We have to think about how big are polar sets. Yeah.
But would that mean that our polar set is dense?
No. Again, X is just some curve. There's the picture is someplace. There it is up there. It's that pink curve. Yeah? Okay, let's think what a meromorphic function, we're going to talk about this in detail right now, but think what a meromorphic function is. In general, it's f divided by g locally, right? And the bad set is where g equals 0, right? In complex analysis in one dimension, g equals 0 is a discrete set. It's really a nice thing. But g equals 0 is codimension 1 always, it's one equation. So in two variables, it's going to be a curve, right? And the danger might be that exactly that curve is your X. And okay? You might be unlucky. So I said, this is what I said, if you're not unlucky. Because hardly ever that'll be the case, right? I mean, usually for most G, if you restrict it, it won't, and you have to be incredibly unlucky that you exactly hit X with the zeros of G. Okay? You have to be incredibly unlucky. Okay? Okay. So, that's interesting. So we asked the question, what are the meromorphic functions on P2? Because we want to restrict them and get nice meromorphic functions on the Riemann surface. So far we have this Fermat surface of some genus. I don't know what it is. We don't even know there's a meromorphic function, but if we're going to, if we can restrict these meromorphic functions, we get a lot of them. So let's do an example. So the theme is then, the first theme is, that was point number 3, 3A. Describe the meromorphic functions on P2. So we hope we get a lot of them. Well, let's see. What do we have on P2? Well, let's try something. Let's try a polynomial of degree D in 3 variables. For example, let's try, I don't care, Z1 to the, and here's one, Z1, Z2 to the D minus times Z3. Now we don't have the degree big enough. Let's make it big to the D minus 2. That's a polynomial of degree D. Right? That's a polynomial of degree D. This is not a function on P2. It's almost a function on P2. on P2, almost a function on P2. The reason it's not quite a function is PD, we know, PD of lambda times the vector is equal to lambda to the d times the vector. It's not well defined. It's not well defined because these are homogeneous coordinates. So this is not well defined. So it's not quite well defined. This is where physicists are much better than mathematicians. They write down something that they think is natural, and it's not well defined. It doesn't make any sense at all, really, but it almost makes sense. And then once it almost makes sense, you have to fix it. Okay, so we fix it. So fix it. And the way to fix it is take another polynomial of degree d, another one. Another one. A polynomial of degree d. Take another one. Well, let's take another one. I say, for example, I don't know. I don't care. Let's take the Fermat one. I don't care. Z1d plus. It doesn't matter. Let's take the Fermat one. Doesn't matter. And then you have the courage as a physicist to write down P divided by Q. And you want to check that it makes sense. Let's see if it makes sense. This is a question. So we see M of lambda V equals P of lambda V over Q of lambda V, and this is lambda to the d comes outside P of V over lambda to the d comes outside Q here, and the lambdas cancel. This is equal to P of V over Q of V. Yeah.
So the reason why we say it's not quite well defined in the uppercase is that it should give us the same, since we're talking about...
It should be a function.
Yeah.
If you want it to be, yeah, okay. So, you're talking about here, yeah. So, don't forget, the coordinates here are homogeneous coordinates. And these homogeneous coordinates are really coordinates upstairs in the principal bundle. So when you're changing basis, you're multiplying by lambda. But, you know, it's a stupid change of basis, but it makes a big difference. And if you just write down a function of these three variables, it's well defined upstairs in the vector space, but it certainly is not defined on the projective space.
I see. Because P of lambda V should be the same as P of V.
It shouldn't make a difference. And upstairs, what do we care? I mean, we don't care. It's just some function. But downstairs, we care. Otherwise, it's not well defined. And so what we do is we take care of this problem by dividing by another thing that transforms in the same way. Okay? So it's a fundamental principle of mathematics. Write down something that transforms in some way that's not well defined, and divide by something else that transforms in the same way, and you kill off the transformation rule. Okay? This is the fundamental principle. So this is really well defined. And if you like, let's look at it. So it's in this example, it doesn't matter, of course. Z2, Z3, D minus 2 divided by the Fermat D plus D1, D2, D3. And now that you want to analyze that guy. Don't quit here, you're not finished. You want to analyze this guy. So for example, if Z1 is not equal to 0, then what we do is we have Z2 over Z1. This is equal zeta 1. And Z3 over Z1, this is equal to zeta, I don't know what this is. This is equal to eta 1. Right? And now now I'm going to write this, I'm going to divide both sides of this up and down by z1 to the d. At the top I get, dividing here, I get, divided by that, I get zeta 1, and here I get eta 1. I'm sorry. I put the index upstairs, I was probably stupid. 2 to the d minus 2 divided by 1 plus zeta 1 to the d plus eta 1 to the d. And the in coordinates, I've written down a quotient of 2 holomorphic functions in coordinates. Yeah. Of course, I can only do that if z1 is not equal to 0, but then if z2 is not equal to 0, I can do the same thing for z2. I just divide by z2 to the d. Right? So this process here is called, this is the homogeneous level. This is the homogeneous level, and this process is called it's a terrible word, I don't even know how to spell it. I don't know. Dehomogenization. You have it in a homogeneous level, and you divide out in the coordinate chart, and you get it dehomogenized. Dehomogenization. Something like that. Okay? And there you are. That's a meromorphic function. Okay? So you see then if you have, so you're given x in B2, yeah, and x is the zero set of some polynomial. Let's not call it p. Let's call it p sub x equals 0. Some polynomial of degree d. It doesn't matter, some homogeneous polynomial, I don't care what degree it is, it's some degree, and it's in there, and then I take the meromorphic function, which is, say, p divided by q of the same degree, I don't care, but the key is that q equals 0 is not identically 0 on x. Right? And so that's a question of whether or not this polynomial divides q or not. So it's not a very hard question much in P2. So the key is that this is what we talked about it before, that this thing does not vanish identically on x. That's a statement, that's that statement, and of course that's a statement that related to whether or not these things are relatively strong. Of course, x could be singular, and you could have 2 components, and maybe I'm not considering that case. I'm considering the smooth case. Maybe the danger would be it's identically 0 on one component and not on the other. So that could happen as a general principle, but I'm considering only smooth things. So you get tremendous amount of meromorphic functions by restriction. Okay. Now we come to my last part that I haven't discussed in sufficient detail, is what about P1? X equal P1C. Okay. Well, let's look at it. Motivated by the above example, we consider just meromorphic functions and a polynomial. Now I'll write the variables, because if let's write the variables here: homogeneous coordinates z1, z2. Yeah? And so at least here we should have homogeneous polynomials of degree d in these two variables. Yeah? And let's then look at this the way classical mathematicians look at this. I can't remember, maybe you can tell me if I go to, that's homogeneous, and if Z2 is not equal to 0, then I can write this as Z1 over Z2 and 1, and that the coordinate then is Z1 over Z2, and I think I'm calling this coordinate Z. It's a choice, okay? And if you have this thing when Z1 is not equal to 0, then you can divide by Z1, so you get this thing. And this coordinate then is Z2 over Z1, and I'm calling this coordinate zeta. And I think that's the notation of Riemann, these two coordinates. And as you see in a stupid way, zeta is equal to 1 over z, so this is the usual change of coordinates in V1. And just for fun, if PD, say it's PD is, for example, a cubic, so it's Z1 cubed plus, say, Z2 cubed, and the bottom, let's make just a stupid example, Z1, Z2 squared, that's a cubic. A cubic, this is the quotient of two cubics. Same principle, it's a meromorphic function. If I divide by z, the first line I divided by z2, so let's divide by z2 cubed. I get, dividing here I get 1, dividing here I get z cubed plus 1 over, divided by z2 cubed over z. Right? You get what I'm doing? I'm dehomogenizing that thing, just dividing by z, yeah? Well, that's a ratio of two things that you know about, right? And in kindergarten, you call this thing a rational function. Right? It's a rational function, and you see, this is the version of it on the z-plane. Okay? And so, but we don't know about what's going on the zeta plane, because we chose the z plane to think about. In the zeta plane, zeta equals 0 is what we call infinity, so we want to know what happens at infinity. So what happens at infinity is of interest. So we divide, in that case, what we just tried dividing by zeta, z1. No. I divided by z2. Did I do it right? I divided by z2 cubed. Right? And now I want to divide by z1 cubed, so I can dehomogenize. That verb I can say, dehomogenize. Dehomogenize is easy to say, but dehomogenization is hard for me to say. It's funny, and these words like this are easier to say in German. Dehomogenisierung. Somehow it's easier because every word in German is long, so you're used to it. So let's just for the heck of it try it. So in the zeta plane, That means you divide top and bottom to dehomogenize by Z1. And I divide top by Z1, I get the meromorphic function, it doesn't change on top, it's lucky 1 plus zeta's cubed over, and now top and bottom by Z1 over zeta squared. Yeah? So, right, that's right. Right. So you see this thing has, this thing, if you write down its Laurent, its principal part, it's at infinity, it's the principal part is 1 over zeta squared plus holomorphic part. So it's a very interesting thing. There's a pole of order 2 at infinity with no residue. That's what you should always do. Dehomogenize and deal with infinity, and it's a pole, no residue, it's really great. Let's look at this guy. At the origin, it has a pole of order 1. Okay, it's a pole of order 1. Where are all the poles here? I must have made some mistake here. Do you think I made a mistake? I only see one. Oh, no. How many poles does this guy have? How many poles does this guy have? 2, but you're wrong, 3. There's a pole of order 2 at infinity. So you count the degree of the polar divisor of this thing is 3, right? And we better have, as you know, 3 zeros also, because we proved this. Yeah, the degree of on a compact Riemann surface, the degree of the divisor is 0, total degree. So we have 3 poles, a pole of order 2 at infinity, and you see these trivial things you should do for yourself. So here is infinity, and we have a pole of order 2, and here is 0, and we have a pole of order 1. And now I have to figure out where the devil the zeros of this thing are. Well, the zeros, that's great. The zeros are where the top is 0. And that's just the Fermat thing, that's the roots of unity, basically, up to this time. Yeah. So you see, that's Z1 cubed plus Z2 cubed equals 0. That'll be the, I don't know, that'll be the 3 roots of unity around here, someplace like this. Yeah. So, and these are simple, these are poles, pole of order 2, pole of order 1, and then here we have 3 zeros, some another 0 of order 1, and a 0 of order 1, and a 0 of order 1. Here, another 0 of order 1. And that's exactly what it should be, because the number of poles should be equal to the number of zeros in the compact Riemann surface. That's what it is, and that's the okay. Now, conversely, I see Crystal back there. She says, okay, you gave me an example of something here. Yeah. Now tell me what everyone is. So M is now arbitrary. And then she asks the naive question, it's a good naive question, how does it look? This is a good question, right? This is a warm-up calculation, and now a good question. You ask the question, how does it look? Right? Well, it's the degree of the divisor of M, we proved this, on a compact Riemann surface, is 0. This is the state we proved this. Yeah? It means it has the same number of poles as it does zeros. Right? So that means we have the number of poles, and of course when I write, I mean that the polar divisor. So the divisor, let's call this divisor here D, and this divisor D is the zero divisor minus the polar divisor, right? And the degree of the zero divisor is the same thing as the degree of the polar divisor. Here we had three, well, three, because 2 plus 1 is 3, here 1 plus 1 plus 1 is 3. That's the same thing here, right? So all you have to do is, to answer Crystal's question, is take P, a homogeneous polynomial of degree, let's call this thing D. Take P of PD with the divisor of PD equal B plus, and take QD with the divisor of QD equal D minus. Right? I just set it up that way. That's to take two homogeneous polynomials, that's what you get. And then I look at PD divided by QD. Okay? Well, let's look at this. If you don't believe me that this is equal to M, you're probably right. You shouldn't believe me. But I divide this by M. Okay? And if I divide this by M, this thing has no zeros and no poles. Because this thing here has the same number of, the same poles as M does and the same zeros as M does. I divide by M, I kill everything. This has no zeros, no poles. This is therefore a constant. Right? So that says the PD over QD is up to a constant equal to M. Right? And that says then that the meromorphic functions on the Riemann surface, which is P1C, is, and now you should think abstractly and concretely. And abstractly, it should be the quotient field of the functions of two variables. So let me write it down of the polynomials in two variables, where V, these are the polynomials on V, and V here is equal to, V is equal to C2. Right? So a quotient of polynomials. Right? Or you could take, of course, PD, I don't know, PD1 over QD1 and plus PD2 over QD2. Yeah? I mean, you could write stuff like that. So what this is if I want to emphasize what this really is, this thing is, I write it down as the graded quotient field over D of the polynomials, the homogeneous polynomials. So you're taking the quotients that you're taking are quotients of homogeneous polynomials. Yeah. Otherwise it doesn't make sense. Okay. So that's really what's going on here. And as we've just seen, if you divide out, this is the rational functions in Z. In the variable Z. Remember what I did it only in the example, but anybody can do this example. You just have to divide by the right thing and you get the rational functions in Z. So this is nothing. And the notation for the rational functions in Z is this C, and with round brackets, that's the rational functions in Z. Okay. And therefore P1C is called a rational manifold. Okay, because it has a rational function. Now this is more or less trivial, right? I mean, you just say, well, you have to have the same number of zeros as poles. You write down the two polynomials with the zeros and the poles. You write down the ratio, and you find out it's the same thing, and that's it, right? So it's almost trivial, but it's a fundamental fact. I hear a question, yes.
Oh, so then in our example, which were the poles and the zeros? So if you just have and this one.
Oh, okay. Yeah. It's very, very nice. Suppose that's what he's testing me, and it's a good test. Suppose you start with this picture, and I should be able to reproduce The ratio.
I mean, for our example, like if our Merrimack function is given as on this blackboard, we say the poles are at 0, and
I'm not sure what your question, you're gonna tell me where to stop. Okay,
I mean, if,
here's P1C. Okay, you give me a meromorphic function.
for example, with the one which we wrote, that 1 over zeta squared plus something homomorphic.
Okay, you happen to write that down in the zeta coordinate. Okay, and so the zeta coordinate, here's, what is infinity? Here's this is zeta equals 0. Yeah, and this means that it should have a pole of order 2 here. Yeah, and now here's 0, so zeta doesn't know what 0 is, so this is z equals 1 over zeta. So it has a pole, yeah?
Why is that a pole?
Well, oh, why is this a pole?
Yeah, why is...
I have to change coordinates. So this changing coordinates, I get z squared plus 1 over z.
Okay, I think I see. So we have to consider both, so in both coordinates.
If
Because it depends on where on the manifold we are.
yes, of course, it's a manifold, so you have coordinates, but you're the one who wants me to do this in coordinates, and I'm happy to do that. But what I said, I prefer doing homogeneous coordinates, because then I don't have to pick up all these coordinate stuff. It gets on my nerves. So I write down the top to have the zeros and the bottom to have the pole. And writing down homogeneous polynomials with the right zero set is a joke, right? That's what we did here. I mean, you give me the coordinates, I can do it. But what I prefer to do is do this. Is this what we had here? I'm not sure. No, here it is. You say that we should have zeros at those 3 points on the unit circle, and so I write this guy down. And you said we should have poles at those points, and so I write this guy down. See, if you look at that, the poles are where these things are 0. That's z1 equals 0. That's maybe down here, and z2 equals 0. That's up there, but it's much easier doing homogeneous stuff than it is changing coordinates all the time. So it's a good question. Thanks. Let's take a break until exactly at 2, okay? So, no, 1, I'm terribly sorry.